Hey, Honors Physics, we're going to take a look at the highest level of problems, the most difficult level of problems, before we add friction and before we add inclined planes. What I mean by that is we have yet to tackle the physics of how do forces work when you're on slopes like this, or when, for example, you have an object moving in a linear direction, left or right, and we have a significant amount of friction. And we're going to tackle that right after the Thanksgiving holiday. So let's start. So the final kind of problems that we're going to be dealing with have to do with kind of what we might call box problems or crates. And you're like, that seems so specific. Well, what I mean by that is if you have an object and you're examining forces in 2 dimensions, and you're looking at the system from the top, right? The system is just one object, and we're examining it from the top view. And what I mean by that is that there are certainly forces, right? If I were to turn this into the side view, wouldn't there be a gravity force that's going down into the page? And there's a normal force going up out of the page, right? Because if we're in top view, right, I'm kind of turning it to sideways. These 2 forces, if you're sitting on a table or a floor, these 2 forces are in equilibrium. So let's call that, and we're going to actually call it the z-axis, right? So the z-axis, they add up to 0. But what we have, let me kind of clean this up here, is we actually have other forces that are now in the x and y direction, right? Z being the 3rd dimension. And what we mean by that is we now finally have forces that are not just up or down or left or right. We have a force that's at a 45-degree angle, 60 newtons, and then we have a force that's at a 0-degree angle of 40 newtons. And both of those, 40 newtons, not 40 degrees. And what we will have to do is we're going to have to find components by adding up all of the x forces or x components and adding up all the y components. Once we have that, we can find the net force by recombining them. That's the Pythagorean theorem. How do you add vectors that are in the x and y? And that's, of course, the Pythagorean theorem to find the hypotenuse. So let's call that the resultant force or the net force. And then how do you find the acceleration of that system? Well, then you use Newton's second law. But what force are you going to use? I think I slightly covered it, but essentially it's going to be the resultant force of all of your x's and all your y's divided by the mass. So really all it adds is 2 dimensions to the problem. The next kind of problem is a side view of that same box, but something really interesting is happening, right? We have multiple forces, and they're not just left and right or up and down. We've got a gravity force and we have a normal force. And we're going to really find out that the normal force is actually one of the more tricky forces to find here. I'll show you the system, but it's going to be kind of the challenge, right? That's going to be the harder part. Now, what are these forces? These might be applied forces. One force is pushing the box or the crate down and into the table. One is kind of pulling it up. And we're going to try to find of course, the total force, and we're going to try to find the acceleration. Now, what you may notice, though, is that if you're looking at the side view of a crate right here, right, and you have all these forces, the motion is only ever going to be in the x direction because the normal force we found out will adjust itself to balance out all of the up forces and down forces. Remember in the elevator activity, the normal force is dynamic. Or, the word I like to use, it's always sufficient to balance out the vertical components of this applied force, the vertical component of this downward or angled force, and of course gravity. So we'll take a look at how to do those. Lastly, the most challenging one, although it's in many ways kind of the most fun, is what we might call concatenated systems. Really what it is a system of multiple objects, and what they do, this is a system, and what they do is they have a single acceleration, right? They have an acceleration that is common to all. And you say, well, wait a minute, those buckets are not going to accelerate at all. They're just hanging from a ceiling. Correct. They have an acceleration of 0. Other systems, maybe something pulled sideways. Picture like a kid's toy where you're pulling along trains on a string. It's an old-fashioned kind of toy. And this system is going to have an acceleration, but who has the acceleration? Well, if this is the external force, this object and this small one, A and B, are both going to accelerate the same. Now, if it's pushed from the other side, inward as opposed to being pulled, right? Again, these two blocks are going to accelerate the same. Okay, so let's take a look at sample problems, okay? In fact, we're going to start with a concatenated system. So we've got a 3 kilogram bucket, and we've got another 3 kilogram bucket. And if you were to do the force diagram for each individual one, you might remember we did this in a station. We've got tension, and we've got gravity. But the tension on the top is definitely not the same as on the bottom. The upper tension has to hold the whole system. So let's call that FT1 and FT2. And then on the bottom, we've got an FT2, and we have a force of gravity. So that's kind of the picture that we have. Now, what other information do we have? All we know is that the buckets are at rest, and they're balanced, right? They're in equilibrium, right? There is no net force on the system. They're hanging, and therefore the acceleration is 0, right? So they have a static equilibrium because they're at rest and their forces are balanced. So it says if the buckets are pulled upward with an acceleration of 1.6 meters per second, I guess someone must be pulling on that rope, calculate the tension in each one. Okay. So do you see the problem? Is that, the upper one has 2 tensions, the bottom one has only 1. So here's a suggestion. There's multiple ways to tackle this, but what I might suggest is you concatenate. Concatenate means treat the system as one object, 6 kilograms. If you do that, if you were essentially to get rid of this string in the middle, then there would be only one force of tension above, and there'd be one force of gravity. How would we find that? Well, we'd have 6 kilograms times -10 or -60 newtons. And we don't know the tension force, but that's what we're asked for. And do you see what happens here? It's kind of nice. You say, I know the acceleration, and Newton's second law says that if you know the acceleration is 1.6 meters per second, positive, and the mass is 6, and the sum of the forces are FT1 plus FG, -60, right? FT1, what's 6 times 1.6? A little over 7. 6 times 1.6. I should do that in my head. Oh my gosh, no it's not, because 6 times 6 is 3. My fault. 9.6 newtons. Then you have to add 60 to both sides. I don't want to make mistakes, because I sometimes do. And there we have force tension 1. And you're like, oh, maybe some of you would have thought of doing that all by yourself, but now we found FT1. Okay, and that's above the first bucket. And you say, but we didn't do the physics of the 2 separate buckets. Correct. But if you kind of pretend the bottom string doesn't exist, it simplifies the free body diagram. Now, if you want to find forces that are in the middle between the 2 objects, then you have to do what's called discrete analysis. You separate the objects. And I would actually suggest that we focus on, if you want to find FT2, right? So we found FT1. But if your target is to find FT2, what we notice is that if you look at the bottom bucket, it has a much simpler free body diagram, FT2, FG. This FG is -30 newtons because 3 times -10, and we don't know FT2. And if you do the second law for the discrete object, right, discrete analysis. If you go into any applied science, you might see that there's actually far more to discrete analysis, but you're basically figuring out how each component operates. That's what discrete means in this case. And we've got FT2 plus FG equals MA, 3 kilograms times positive 1.6 equals, what did we say FG was? -30, FT2. Okay, let me kind of zoom in so we can see it a little better. And what do we have? 3 times 1.6 plus 30, and we get 34. And look how it works out. The bottom tension was less, right? The tension between them, 34.8 versus 69.6. So that's how you do concatenated systems, and I'm going to do a separate recording for how to do the box problems.